And incidentally, all of the recordings that we've had so far, I've, as of including last Friday, I've put in closed captions as well. Just out of curiosity, do any of you find the closed captions helpful with the video? Does anybody, turn them on, or do most of you? Oh, okay, okay, wow, okay, great. Well, that's great to hear. Thank you, thank you. All right, well, it's a bit of work to get those captions in, but it makes me feel good that it's helpful to you all, and thank you. Um, okay, so this is another problem uh, that deals with Newton's law of cooling. So I'm going to let you copy this example down, okay, and then we'll look at the example. Okay, so in this problem, uh, we have a bottle of soda pop at room temperature is placed in a refrigerator where the temperature is 44 degrees Fahrenheit. After half an hour, the soda pop has cooled to 61 degrees Fahrenheit. Okay, so that makes sense. You put the bottle of soda pop in the fridge, it's going to start to cool. The question is, how long does it take for the soda pop to cool to 50 degrees Fahrenheit? Okay, does anybody know what special principle we have to use to solve this problem? It's a special law. So of course we need the differential equation. We need a differential equation in order to solve this problem. That's right, and Robin's right. We need to utilize what's called Newton's law of cooling. Newton's law of cooling. So let's go ahead and get to the solution. Everybody has the example copied okay? Okay, let's go ahead and get to the thing here. So what we do is we define big T, capital T of T, little t, where little t's time, that's going to be the temperature of the soda pop after T minutes. We always have to specify our units, okay? By Newton's law of cooling, the rate, let's say this the right way here. Well, I'll let you copy that at the top. Okay, so by Newton's law of cooling, the rate at which the soda pop's temperature cools with respect to time is proportional to the difference between the temperature of the soda pop at time t and the ambient temperature of, I want to be careful, no, the temperature of the refrigerator. Right, the temperature of the refrigerator, which I believe that's called ambient temperature. When you have an ambient temperature of surroundings, in this case, the refrigerator is our surrounding. I mean, that's what we're interested in. It's 44 degrees. Okay. All right. So, you know, I'll go back, but, well, so whenever you have one of these type problems where, like, a cup of coffee is cooling down or turkey is heating up, you put it, you have a turkey, you put it in the oven, it starts to heat up. These kind of problems involve Newton's law of cooling. So the change in temperature with respect to time is proportional to the difference between the temperature of your object at time t and the ambient temperature of whether it's the refrigerator or the oven or whatever. Now, what they do in the book is they decide to use a substitution. If this example is actually worked out in the book, it's the fourth example in section 7.4. And what they do is they say let y equal, they make a substitution, let y equals t minus 44, and then dy equals dt, or I should say dy dt equals d big T dt. And so this differential equation gets converted into dy dt equals k times y, because y was t minus 44. So they can rewrite the differential equation as dy dt equals k times y. And then they proceed on with the problem solving for y. And then once you solve for y, you go back and substitute it in the t minus 44 for y. And that's okay to do the problem that way. But I look at this problem and I'm just more comfortable right here separating the variables. So if we separate the variables, 1 over t minus 44 dt equals k dt. And therefore, the integral of 1 over t minus 44 dt, and this t here, this t, right, is a capital T, it's not a lowercase t. That equals the integral of k dt. Okay, now we could use a substitution here. right? We could let like u equals t minus 44 and do a little substitution to integrate this, but I don't think it's that hard to see that the antiderivative of the left side here is going to be the log of the absolute value of t minus 44. If you differentiate the log of the absolute value of t minus 44, you're going to get this integrand here. Because the derivative of the log, that's 1 over t minus 44, and then the derivative of t then by the chain rule is just 1. So, but now that we've in it and you integrate the right side, you get kt. So you have the log of the absolute value of t minus 44 equals kt plus c1. You notice I do both my integrals at the same time. That way, it just seems a little cleaner to me to do it at the same time. Remember notation too. You always have to have your differentials. A few of you I notice are doing integrals and leaving off the differentials in your work, and I point that out. Also too, the integral needs to be in front of the integrand. Occasionally I'll see notation like this. I think I saw something like that, and that's not correct notation, right? That's not correct notation. This is the notation you want to use. So okay. Now now we're down here to this stage. What would you want to do next? What might be a good thing to do next? We want to solve this for t, right? We're looking for our and that's right. Gabriel's right. We want to raise the expression by e. We want to exponentiate both sides. But I'll note that we don't need the absolute value for this particular problem, because hold on, let me go down a little bit more. Hold on. Yeah, the temperature of the soda pop is going to cool down to what the fridge temperature is. But the temperature of the soda pop is going to always be more than 44 degrees Fahrenheit, right? Because the soda pop starts out at 72 degrees. You put it in the refrigerator, it's going to cool down to 44 degrees in the fridge, because the fridge's temperature is 44 degrees. But it's never going to go below 44 degrees. So there's no chance that t minus 44 is going to be negative. And also, we can make the assumption that, hey, the temperature of the soda pop will always be a little more than 44 degrees. It's okay, to make that assumption. Maybe in a month's time, the temperature of the soda pop would be 44.00001 degrees Fahrenheit. I mean, you see, I think, where I'm coming from here. So, okay, now we exponentiate both sides. And you've had practice doing this from your homework, your section 7.3 homework. E to the kt plus c1 is the same as e to the c1 times e to the kt. And what I'll do now is I'll call e to the c1 power, I'll call that my new constant c. Okay, so you can't say e to the c1 power is c1. You have to call it a new constant. All right, and I look for those kind of things in your work. Now we're able to solve for t. And are there any questions up to this stage here? Are there any questions at all? Okay, all right. So this expression for the temperature of the soda pop right now we know is we can't use it because we have two unknown constants here. In order to use this expression, we need to solve for those unknown constants. So we need to use two pieces of information, two initial conditions. What's one of the initial conditions? What's one of the initial conditions? What about initially at t equals 0? That's right. The soda pop is, that's right, Gabriel and John. The soda pop is equal to 72 degrees Fahrenheit. So we can put in 72. That corresponds to t equals 0. And we can solve for c. We get c equals 28. And so the temperature is equal to 44 plus 28 times e to the kt power. That is a k there, right? That is a k. Okay. Well, now what's the other what's the other initial condition here? Just wanted to sharpen my pencil and make that correction on my paper. What's the other initial condition that's given in the problem regarding the soda? Well, Robin, you're almost right. The 61 is very important. T of what equals 61? Almost right. That's right. That's right, John. So after 30 minutes, the soda pop cools to 61 degrees. Okay, and so now, here we are, we're right here, and we're going to use that because t of 30 minutes equals 61. Okay, so, all right, let's go to the next page. And, 61 is then equal to 44 plus 28 times e to the k times 30. And Robin and John were right to recognize that, hey, hours have to be converted into minutes. And so you work out the math, and you're going to get k equals the log of 17 over 28. And you have to take your decimal, you have to take that decimal k out far enough so that you have enough digits, because WebAssign is going to be very picky regarding the answer. Okay. So I took this out to 5 decimal places. Now, of course, if you get an answer and WebAssign doesn't take the answer, try going out to like maybe 8 decimal places. I'm just 5 because it's in the book, But the reason I have a tight numerical tolerance limits on answers is because sometimes students, they'll do a problem wrong, but yet they'll, by accident, get the right answer. That can happen. But if the numerical tolerance is very tight, then pretty much you have to do the problem the right way in order to get the right answer. Although occasionally, though, a student can luck out. And I don't know if I'd call it lucky, but occasionally a student can get the right answer doing it the wrong way, but it happens a lot less with the tight numerical tolerance. Okay, so now we have K. We know what K is. So our temperature function with respect to time in minutes is 44 plus 28 times e to the negative 0.01663 t. And so now that we know that, we are able, well, the question asked, how long does it take for the soda pop to cool to 50 degrees? Well, if they're asking how long does it take, that means we're looking to solve for time, T. It's the big temperature T, that's 50. So what we have to do is set 50 equal to the 44 plus 28, e to the negative 0.0016663 t, and we have to solve for t. And this is like pre-calculus skills here. Obviously, you're just going to work the math out. Just work the math out, and t, lowercase t, will equal the log of 6 over 28 divided by negative 0.01633. Okay. And you're going to get 92.6 minutes for t. So if WebAssign said round your answer to one decimal place, that would be your answer. Are there any questions up to our answer here? Okay, well, I'd like to move on to the next page. You notice here that the K was negative, right? The K is negative, and that makes sense here, because this is basically an exponential decay type problem. If the soda pop cools to 50 degrees Fahrenheit after about 1 hour and 33 minutes. 92.6 minutes is about 1 hour and 33 minutes. And we'll notice that based on the formula, if you think about the formula here, right, this formula here, as t goes to infinity, if you were to think about, what temperature does the soda pop reach after a long, long time, let t goes to infinity? Well, as t goes to infinity, this term here, this exponential term, is going to approach 0, right? Because as t goes to infinity, you're going to have e to the negative infinity, and that approaches 0. And what I have here too is just from the book, I drew a picture of the temperature function. Okay, we graphed the temperature function, which is 44 plus 28 times e to the negative 0.01663 t. That's graphed right here. And you can see initially the temperature of the can of the soda pop is 72 degrees, and it will exponentially go down in time to 44 degrees. But doesn't go below it, right? It makes sense. Okay. How many, and you can see in the beginning, the exponential decay is fairly rapid, like between 0 and 30 minutes, the soda pop cools fairly quickly. But then after time, the soda pop, it cools, but its rate slows down. How many notice that from real life? when you put something in the fridge, something like a bottle of soda pop. It cools kind of quickly in the beginning, but then it kind of, you know, I mean, if you, yeah, yeah, Josiah and John know what I'm talking about. If you want it like really cool to the fridge temperature, you gotta have that thing in like maybe what, half a day, something like that. How many noticed that? I certainly have. I certainly have. Yeah, Raymond knows. Thank you, Raymond. Um, okay, there's another example from section 7.4. And again, I did it a little bit differently in the book, but I kind of like the way I do it just because, um, I just like my approach, But all right, let me stop the recording.